So let's first talk about current. So we're going to do one by one. Okay, so what is current? Current is the rate of flow of charge. Okay, so what is rate of flow of charge? That means how fast the current is flowing. So from here, there are three separate formulas that we're going to learn. The first one is this, which is current is N times Q over T. So in this case, your N here refers to number of electrons. Q here refers to the charge of each electron, for example, and T will be the time taken. But of course, you can actually use any type of charge. For example, if you're talking about proton, then this will be a charge of proton, this will be number of protons. Or maybe it could be alpha particles. That means this will be number of alpha particles, and this Q will be the charge of each alpha particle, which is 2 times E. So this formula actually comes from here. You know why? Because Q here represents total charge. And total charge is equivalent to number of particles carrying the charge times the charge of each particle. We multiply, you get total charge flowing. So when do we use this formula? Is when they want to find number of charged particles flowing or number of charged particles flowing per unit time. Then we take current divided by Q. Alright? To get number of particles per unit time, or you just want number, there is not current divided by charge times time. Okay, so this is the first one. So the second one is when we talk about this, and what will happen is you can find the total charge that flows, total charge that flows. So how do you find the total charge that flows? You can take current times the time. But this is provided your current is constant. But your current is not constant, the total charge that flows, you must draw the IT graph first and its area under the IT graph. Okay, so you must do that. Okay. Now there's a third formula which is in your new syllabus. So there's a third formula in your new syllabus. So what's the new formula for your current? The third formula is this. I is equals to NAVQ. So how do we get this formula I equals to NAVQ? I will show you in the next slide. But in this equation, you must be very careful that the N here and the N here doesn't represent the same thing. The N here represents number of charged particles, like for example, number of electrons. But in this formula, I equals to NAVQ, the N here represents number density, which is number of charged particles per unit volume. There's a per unit volume there. Alright, so I will come to how to use this formula in the next slide. Okay, so now we're going to derive a new equation for current. Now, the original formula for current, remember, is I equals to rate of flow of charge. So the Q here represents the total charge flowing, but there's also another quantity that we need to know, which is N, which is called number density. So number density is the number of electrons per unit volume. So for conductors, the N is between 10 to the power of 28 to 10 to the power of 29 electrons per meter cube. That is the number of electrons we have in 1 meter cube. But for semiconductors, you'll find it's about 10 to the power of 23 only. So semiconductors have much smaller number densities than your conductors. So in terms of the number density, we can actually modify the formula. So the total charge here will therefore be the number density, which is number of electrons per unit volume, times the volume, right? So let's say this area is A, and the length here is L, so the volume is A times L, correct? So if the number density times the volume gives you the number of electrons, then you times the charge of the electron, which is E, then you get your total charge. Then you divide by time. But L over T, which is the distance here, divided by time taken, isn't it speed? So that's how we get NAVE. Yeah, that's all. So generally, if you're talking about any other types of charge carriers, then you can modify a bit and call it NA. So the A is big. You can call it NAVQ. If it's not electron, then you use the Q of, which is the charge of the particle that you're using. Understand? So you can either use I equals to NAVE for electrons, or for other types of charges, you use I equals to NAVQ. Which gives us the formula for drift velocity. So what is this V? This is called the drift velocity. So V equals to I over N NAE lah, or NAQ lah, either one lah. So your drift velocity, what are the factors that affect how fast your drift, how fast your electrons will flow? You see the next slide. So we'll write down again, V equals to I over NAQ. Now, so what they're trying to say here is, provided everything else is constant, that means using the same conductor, same area and all those. So what will happen is when you double the current, the speed must be double. So whenever the current is double, that means we are assuming that the charge is flowing at twice the speed. Or if we are talking about the same formula, but now we change the area. Now, assuming that the I is constant, we want the same current here and here, because if this conductor is in series, then the current here must be equal to current here. You cannot have a smaller current here and a bigger current here, because charge is constant. So it all flows, alright, and have the same current. You cannot have different current here and here. So if the current is the same, but this side, the cross-sectional area is halved, so can you see your V is inversely proportional to A? So you halve the area, that means this section must be traveling at twice the speed. Okay now. And finally, the effect of using the different number density lah. So if you want to maintain the same current, but the number density is smaller, that means instead of using a conductor, we use a semiconductor, but we want to maintain the same current, so what must happen? Your speed will increase. Because this is constant, this one becomes smaller, so this one over a smaller value gives you a higher speed. So therefore, in a semiconductor, they should be moving faster. The electrons must be moving faster for the same current. So that's the conclusion.